Hello one more time. Today we're going to talk about the geometry of molecules. So if you went through the chapters about hybridization and about resonance, you will know that if we consider the number of bonds that the central atom in a molecule has and the number of electron pairs, it can have a 3D structure of a different type. This is very important to know, mostly because sometimes we'll have molecules which are not polar, even though the bonds in them are polar. Let me show you what I mean. So if we have, for example, HCl, so this is HCl, let's include the electron pairs. And now here we know Cl has a bigger electronegativity, so this side will be negative, this side will be positive. And it's clear that this is a dipole, so this side will go like this, right? So this is a dipole. However, if we have a more complex molecule which has one central atom and something around it, such as, say, CH4, watch this. So the way you draw this in 2D would have to be like this. So this is the Lewis formula, right? Now, when we have C and H, that's not a big problem because C and H have almost the same electronegativity, so we know this thing is not polar. However, how about if we have CH2, Cl2? Now, you might draw this in this way, like this. Now, what you have now is a structure where you have Cl's, two of the Cl's, which have a high electronegativity. So you would think that this is a minus here, and this is a minus here. So you have two Cl's pulling the central C on two different sides, and they basically would cancel each other out because they're pulling on exactly the opposite side. And even though this bond is polar and this bond is polar, then this whole molecule will not be polar. So this would be non-polar. However, in 3D, we know that this doesn't really look like that. So the actual CH2, Cl2 will have a geometry that looks like, let's find it, like that, like this. So then you see, if even if you draw it like this, if you draw it like this in 2D, how it actually looks like in 3D would be like this. So if one Cl would be here, the other one will have to be either here, here, or here. But in any whatever the other Cl is, you will not have a symmetrical molecule where you have two Cl's pulling opposite. So this molecule would have to be polar because Cl here and Cl here means that this lower side would be negative, right? And the upper side will be positive. So you would have a polar molecule. You would have a dipole. One side would be plus, one side would be minus. That's why it's really important to learn how these things look like in 3D. And this is a really good chapter in the book, so we're just gonna follow the book for this one, so you can see this is real page 416. How do we do this? They have some nice examples here, actually. So look at this, BeCl2. So they give you BeCl2 and they ask you, are the bonds polar? Is the molecule polar or what? So Be, if you remember, I mentioned Be and B. Look at this. Be is here. That's group 2. So, but Be doesn't need 8 electrons. So Be and B are actually exemptions to the octet rule. So B only needs 2 bonds, only needs 4 electrons to be stable, and B only needs 3 bonds. So it means 6 electrons to be stable. So Be will just overlap one orbital with Cl, overlap one orbital with the other Cl, and it will build this kind of structure, and you would have an angle of 180 degrees here. This structure is called, I mean, you will see later how it's called, doesn't matter now. For now, just observe it like this. Then you have BF3. Again, pay attention to B and B because they love to give this in AP because they're exceptions. So B can build 3 bonds like this. But of course, look at this. Again, Lewis formulas sometimes can be so misleading. Because if you look at it like this will be polar because this fluorine has bigger electronegativity than B and will pull this molecule this way. This F also, this F also. So you have pulling here, pulling here, pulling here. So you'll have this side of the molecule that will be negative and the downside, this side will be positive, right? However, this molecule is not polar because actually in 3D, it looks like this. How can you know this? Well, simple rules, guys. The same rules that we use when we talked about hybridization. So the bonds want to get away from each other just because of Coulomb's rules, because of minus and minus repelling. So these bonds are made of electrons. They want to get away from each other. So they won't stay like this. They will go like this. So they can be the most far away from each other that they can. And if you have a free electron pair, you'll see that just in just a minute, that free electron pair will push the bonds even more far away. So this is going to be an angle of 120. But then you have CH4, again, which looks like it's 90 degrees, looks like this, but actually in 3D is like this. We talked about it in hybridization lesson. So 109.5. Then you got NH3. Here you have to be careful because NH3 looks like on paper like BF3. Sounds the same, right? One central atom, 3 hydrogen, 3 fluorines, whatever. So basically, you would expect this to be in one plane, 3 different bonds, but it's not because remember nitrogen also has an electron pair because nitrogen is group 5. So this electron pair will push these 3 bonds down and it will have this structure, even though the Lewis structure of NH3 will look very similar to the Lewis structure of BF3 or BH3, whatever. Then you've got water, which now has 2 bonds but 2 electron pairs. And basically what will happen is just this. It will again have 4 things, but 2 of these things, see, will be electron pairs. And if you look at only the bonds, they will look like this. So this is kind of a bent structure with a angle which is lower than 109.5. You have a bunch of these examples. What you need to learn is this. Unfortunately, this is one of these things that you have to memorize. So this is BeF2, the first example, or BH2, I don't remember, it doesn't really matter. So Be connected with 2 things will look like this, and this structure is called linear. This is BF3. So if the central atom has no electron pair on it, just 3 things bonded with it, it's called trigonal planar. If there are 4 bonds, such as in CH4, you'll have tetrahedral. This is if you have 5 things. So remember we had an example of, I think, PCl5 in the last lesson. So if this is the central atom and you got 4 things around it, they will look like this because this is how they get away from each other the most. This is trigonal pyramidal. This is SF6. So you've got 6 things around it. So you need to remember these because it's going to help us determine which molecule is polar, which is a lot of questions in AP. However, these are just the simple ones. You have these, which I hate so much. I'm having so much trouble remembering them. So you notice that in this table, you've got only the examples where there are no electron pairs. This is just 2 things bonded with something, 3 things bonded with something, 4 things. Here you have the distinction of electron pairs. So you see, tetrahedral is 4 B's bonded with a central A. But if you got 3 B's bonded with central A, and this is a free electron pair, right? This is not a bond. This is such as NH3. So we saw that example. So you'll have a structure that looks the same like this. However, if we only observe the bonds, it will look different, right? And that's called trigonal pyramidal now. It's not called tetrahedral. This is H2O basically. So O has 1 electron pair and another electron pair. So this is just called bent or V-shaped. because if you don't see the electron pairs, it looks like this. These are, on this side, they're actually very rare. You will never actually see this in the lab, but they give these examples and they love to give questions about this. So this is trigonal bipyramidal, the one that you have up here also. See, same thing. However, if there is one electron pair instead of one of these bonds, then you have this structure, which is the most hated structure by all my students, is seesaw. And then you have this one where you have 2 electron pairs and 3 bonds. It's called T-shaped. And the third one is called just linear, see? Because in this case, these 3 electron pairs, they want to get away as far as possible from each other, and this is the configuration that allows it. So it's called linear. Again, understand these are rare, but we do have to remember them because they are really common as examples. So if you continue down, you have these rare examples that will show you how to do, show you some examples that will help you memorize this. This is, for example, helium almost never builds any. Helium is a noble gas, right? It has a stable configuration of 8. Almost never builds anything. But if it does, it can do something like this. This is a very unstable compound, basically doesn't exist. But they love this example. I don't know why. So see, this is 2 electron pairs, one here, one here. Why this one and this one? Because that's the way they get it. They can get as far away from each other as possible, and then 4 bonds like this. Then you have the seesaw. The seesaw. You have this one. So go through this is not that difficult, but please understand that mostly you would want to focus on these standard ones. Standard ones. Seesaw, T-shape, they might give you 1 or 2, but mostly they'll give you tetrahedral, trigonal planar, linear, these here. Okay, I'll give you some examples and some practices. See you soon.